The main steam system in a power plant controls the flow of high-temperature, high-pressure steam as it moves from a boiler to a turbine and is used to drive a generator. To increase overall plant efficiency, some steam is extracted from the turbine and used to heat the feed water for the boiler. The rest of the steam is exhausted from the turbine to a main condenser. Condensate from the main condenser goes through the condensate system and becomes feed water that returns to the boiler through the feed water system. In this way, the condensate and feed water systems work together to supply water at the proper rate to support normal boiler operation. Because the functions of these two systems are interdependent, they're often considered one system, the condensate and feed water system. To maintain normal operation of a power plant's boiler, the water going into the boiler must be equal to the amount of steam that leaves the boiler and enters the main steam system. Keeping the boiler supplied with the proper amount of water is the job of the condensate and feed water system. This simplified illustration shows the arrangement or layout of some of the major components of a typical condensate and feed water system and a main steam system. Included are a boiler, a turbine, a main condenser, a feed water storage tank, and various pumps, heaters, valves, and piping. The area between the main condenser and the suction of this pump, the boiler feed pump, is the condensate side of the system. We'll look at it first. Additional systems are often connected to the basic condensate system that we've just seen. Typically, a chemical addition system is connected to the condensate system. In some cases, however, a chemical addition system may be connected to both the condensate side and the feed water side of the system, or just to the feed water side. In any case, the chemical addition system has equipment for adding chemicals that minimize corrosion and control the pH of the condensate or water. pH is a measure of how acid or alkaline the water is. Usually, a condensate system also has a makeup water system that is connected to the hot well. The makeup water system includes a condensate storage tank and purification equipment that is used to add pure water to the condensate system. The added water compensates for water losses that may occur during normal system operation or from leaks. Finally, various components in the condensate system are also equipped with instruments that measure pressures, temperatures, levels, and flows. These measurements are used in control loops that regulate operation of the system and give operators an indication of how the system is functioning. We've covered the condensate side of the condensate and feed water system. Next, we'll look at the feed water side. Now let's trace the flow of feed water through the system, starting with the boiler feed booster pumps. Not all feed water systems have boiler feed booster pumps, but in this case, there are 3 of them. These pumps increase the pressure of the feed water coming from the intermediate pressure heaters and send the water to the boiler feed pumps. In this example, there are 2 boiler feed pumps. They increase the feed water pressure further so it's high enough for the water to move through the downstream components. From the boiler feed pumps, the feed water enters a series or train of high-pressure feed water heaters. After passing through these heaters, the feed water is ready to go to the boiler. A feed water regulating valve controls the flow of feed water from the high-pressure heaters into the boiler's economizer. The economizer is the section of the boiler where combustion gases leaving the boiler are used to preheat the feed water that is entering the boiler. Finally, as with the condensate system, the feed water system also includes instruments for level, flow, temperature, and pressure indication and control. One more system that we need to look at is the extraction steam system, which serves both sides of the condensate and feed water system. Steam is extracted from the turbine and used as the heating fluid in heaters throughout the condensate and feed water system. Steam from the high-pressure section of the turbine is generally used in the high-pressure feed water heaters. Steam from the intermediate pressure section of the turbine is generally used in the intermediate pressure heaters and in the deaerator. Steam from the low-pressure section of the turbine is used in the low-pressure heaters. Heating the condensate and feed water with the steam from the different sections of the turbine increases overall plant efficiency. Although the examples that we've looked at are typical layouts, there are also many other ways that a condensate and feed water system can be arranged. You'll need to look at your plant's piping and instrumentation diagrams to check the exact layout of the system in your facility. Although the exact arrangement of components in a condensate and feed water system can vary, several pieces of equipment are common to most systems. In this part, we'll look at the major components of a typical condensate and feed water system. We'll begin with the hot well. The hot well is the bottom section of the main condenser. Condensate from the main condenser collects here and is then sent on through the condensate and feed water system, where the temperature and pressure of the condensate are gradually increased. Sight glasses indicate the level in the hot well. A level control loop is used to maintain the correct level of condensate. Maintaining the correct level in the hot well is critical for proper operation of the main condenser. Also, a low level in the hot well could cause the condensate pumps downstream to lose their prime and be damaged. A condensate and feed water system also has several condensers and heaters. Most of these are some type of shell and tube heat exchanger. For example, the initial warming of the condensate from the hot well is achieved by using the condensate as the cooling fluid in condensers. Gland steam condensers recover heat from the steam used in the plant's gland steam system. Air ejector condensers recover heat from the steam in the main condenser's air removal system. Both of these types of condensers are usually shell and tube heat exchangers. A shell and tube heat exchanger has a shell or casing with a bundle of tubes inside. The area that's within the shell and outside of the tubes is called the shell side of the heat exchanger. The area that's within the tubes is called the tube side of the heat exchanger. The heat exchangers that are used as condensers in the condensate and feed water system have condensate in the tube side and steam from the gland steam system or the air removal system in the shell side. During the heat exchange process, the steam is cooled and the condensate in the condensers is heated. U-tube shell and tube heat exchangers are used as heaters to heat the condensate and feed water that moves through the system. Condensate or feed water flows through the tube side of the heater, and extraction steam from the appropriate section of the turbine flows through the shell side. Because the steam doesn't come in contact with the condensate or feed water in the heater is called a closed heater. Some plants have parallel trains or strings of heaters, with several heaters in each train. All the heaters use extraction steam from the turbine to heat condensate or feed water. Typically, to recover the maximum amount of heat from the extraction steam, a train of heaters uses a cascading drain system. In each heater in the train, drips are subcooled by the transfer of heat to the feed water in the heater's drain cooler section. This helps keep the drips from flashing to steam in the drain line. The flow of drips moves from the highest pressure heater to the lower pressure heaters. That is, the drips flow through the normal drain line from one heater into the shell side of the next heater in the train. This heater has a lower temperature and a lower shell side pressure than the first heater has. The drips flash to steam because of the lower pressure within the heater's shell. The drips also mix with the extraction steam that's already in the shell. Thus, the drips are another source of heat to be transferred to the feed water in the tube side of the heater. In our example, the flashing and condensing process for the drips continues through the train of heaters until the drips from the heater that has the lowest shell temperature and pressure flow into the deaerator and become part of the feed water. In other cases, such as in the operation of low-pressure heaters, the drips from the heater with the lowest pressure and temperature flow into the main condenser. The deaerator heats condensate and also helps remove air and non-condensable gases that can cause corrosion. As this cutaway illustration shows, unlike a shell and tube heat exchanger, the deaerator is an open or direct contact heater. That is, condensate is heated when extraction steam and condensate contact each other and mix in the deaerator. As heat is transferred from the steam to the condensate, some of the steam condenses and some of the condensate is heated. This action strips or removes air and other non-condensable gases from the condensate. The heated and deaerated condensate that collects in the bottom of the heater is actually a mixture of condensate and drips from the heater. From the deaerator, the liquid will go to the hot surge tank for storage. From there, it will go on through the condensate and feed water system to the boiler. Air and non-condensable gases that are removed from the condensate flow out of the deaerator through a vent. The vent may vent directly to the atmosphere, or it may connect to the main condenser or to a vent condenser. The hot surge tank, which may also be called a feed water storage tank or a deaerator storage tank, receives the condensate from the bottom of the deaerator. The level of condensate or water in the tank supplies net positive suction head for pumps that have their suction piping connected to the tank. The correct net positive suction head is essential to keep the pumps from being damaged during operation. Also, the volume of water, called the surge volume, contained in the tank is used to meet changes in demand during operation of the condensate and feed water system. For example, if boiler demand increases, the boiler feed pumps begin pumping feed water from the storage tank at a rate that's greater than the rate at which condensate is being fed to the tank by the condensate system. The hot surge tank supplies enough feed water to meet the increased demand for the short time it takes for the condensate flow and the feed water flow to become equal again. Both deaerators and hot surge tanks often have additional connections. Examples are connections from the higher pressure feed water heater's cascading drain system and connections to the vent system from the high pressure heaters.